starting with, like, what was the problem we started with? Actually, it was started long ago at Radies, where the problem of rapid whole genome sequencing was solved using Illumina technology. We at Stanford extended that, created our own pipeline with nanopore sequencing, and in 2021, we showed that we can get a turnaround time of 8 hours or less. One of the important aspects of reducing or accelerating the time to diagnosis was basically a distributed system to do base calling and alignment, and essentially reducing that from doing it locally on the Promethean compute tower, which took about 18 hours for the AG002 data, to bringing it to less than 30 minutes. And for that, we used a lot of GPUs, essentially 64 Tesla V100s, which was then the latest NVIDIA GPUs on the cloud. But that was way back in 2021. A lot of the compute landscape has changed since then. So, as we all know, that as bioinformaticians, we want GPUs in the cloud. Unfortunately, given the rise of Gen AI and the GPU needs that comes with, it's not really possible to find that. So since then, we've had to look at how we can get GPUs for our pipelines. So I essentially went from getting GPUs on demand, 64 V100s whenever I wanted, to about like pinging and trying to find the resources for almost 10 hours. Not ideal when it takes less than 30 minutes after sequencing to actually get the base calling results for a 60x human genome. But the problem was not just getting the GPUs, like essentially, like all of us can reserve instances, but that is not a model applicable for our pipeline. In Gen AI, there is a pretty uniform access needed for both training and inference. It is a predictable timeline, hence reserved instances of huge GPUs make sense and is cost efficient. On the other hand, our ultra-rapid pipeline needed a lot of GPUs for very short bursts of time, let's say just for 2 hours, and it had very unpredictable timelines because you don't know when a patient is admitted to the NICU or the pediatric ICU. So how do we deal with this problem, given that getting latest GPUs was next to impossible, unreliable, and like, frankly, it's a very important use case to just leave getting GPUs to chance. So getting those many GPUs, like one option is just getting it locally, but given that it takes almost a year to get huge GPU boxes, we can't stop our development for that long. But we still can use the local resources available with Promethean and something on the cloud. So instead of transferring all the data to the cloud or transferring all the compute from the local tower to the cloud, we said, what if we have a hybrid model that uses all the GPUs possible? Good. That was one solution. But at the same time, most of the generative AI models, training, inference, requires or uses the latest GPUs, which is something we don't really need. What we need in our case is any GPU where we can do the base calling, and hence we looked at what if we go hybrid, not just in terms of where the compute is performed, but using what resources. So we are using a hybrid model of multiple GPUs to do that. So this slide essentially shows how many GPUs we would need. Of course, with the T4 GPUs being the oldest, and we would require a ton of them, basically multiple GPUs per flow cell, to H100s, which are essentially not available, but like just limited access to it showed us that for superior accuracy base calling, we can basically work with, we would still need 12 to 16 of this like really big workhorses. So sure, this is something, but what we found out that there's a very sweet spot, that there's a very good like sweet spot at the V100 GPUs, which is what we used 3 years ago, but is still the most available GPU on the cloud. And on top of that, we have the Promethean A100 tower, which together gives us like a whole lot of compute that we can work with. So we are combining the cloud resources, mostly the V100 and the L4s, on the good days when we can get the A100s, with the 4 A100 tower that we have available locally. So with this, we do have the overhead of 30 minutes post-sequencing that we can maintain. And we are reducing the average startup time for the cloud resources from 1 hour to 5 minutes. At some point with that 1 hour, we were wasting a lot of money because those resources were not being used. It's like as soon as we have the patient, we start pinging the resources to find out, yes, what's the GPU that we can get? Hopefully, we get it before the sequencing starts. But in this case, now that we are ready to use the older GPUs, even though they are not the most cost efficient, it turns out to be cost efficient because we are not starting them much early on. But yet, given all the analysis, the trade-off, the average cost still increased by 20%. So last year, pretty much on this stage, I had showed that we have the platform Nanopore, where we combined the Ray distributed system management for auto-scaling the resources. Now, what we added to that was continuously polling to find the best resources. So it's like as soon as I'm auto-scaling, whether it is reducing or increasing the resources, I'm looking at what are the best GPUs which are available. Like, of course, starting from the priority of A100s. And that reduced the cost by 30%. So we are essentially lower in cost while maintaining our latency of less than half an hour. We also added heterogeneous, like since we were already looking at heterogeneous resources, we thought about adding variant calling to it. So for example, we run SV calling using sniffles on CPU, and we might use CPU or GPU for deep variant. It depends on what is the cost-benefit analysis. But the good part is now we don't have to do that cost-benefit analysis anymore because Nanopore does it and spins up the resources accordingly. And we also added Spectre for CNV calling. Essentially, at this point, we can add any more variant calling tools that we require to the pipeline without any change to the system architecture, basically saying what is the resource that we would want to use. In terms of quality, like here again, we have the preliminary results because for a lot of because we use deep variant for small variant calling and we do not have a high accuracy model for the, with the newest Dorado and art and chemistry. But we did see that with sniffles, the high accuracy and the superior accuracy models are not too far away. Again, these are preliminary results, but we might be able to reduce the total computational needs in the first place, going from superior accuracy to high accuracy for our clinical pipeline as well. We have, of course, a lot of partners, and the work is done majorly in Professor Ewan Ashley's lab, and my advisor, Professor Mark Horowitz. Methane and John are the two other leads of the project. So thank you so much.